Okay, so starting off this new acids and bases topic, and if we just go back to our acids and bases topic, GCSE ideas. We said an acid is something that makes H plus ions when dissolved in water. We need to refine that a little bit now, because we know, first of all, that H plus ions don't exist really, do they? They don't exist in water because they are actually really H3O plus ions. You can never get just an H plus ion by itself. That would just be like a proton with no electrons. It'd be tiny and very highly charged. So it piggybacks on a water molecule. That's what an H plus ion is. Right, so we're going to change that to our A-level definition. We're going to say, and this is called a Bronsted-Lowry acid. And I think that O should have like one of those funny Danish things going through it, I think, because he was Danish. That's their definition of an acid. And a little bit later on, you probably learn about Lewis acid as well. But Bronsted-Lowry acid is an acid, is a proton donor. And that means a base is a proton acceptor. So if we talked about, if we think about GCSE, what would we be talking about? We'd say HCl, right? We'd say HCl is GCSE. Dissolves in water, that's covalent. So it's an aqueous. It splits up and it forms H plus ions and Cl minus ions. Okay, so it's making H plus ions in solution, and that worked fairly well. But we just refine that a little bit. A-level, what we're going to say now, Bronsted-Lowry theory. Right, we've got HCl, and that, when you put it in water, it reacts with the water to give you an H3O plus ion in aqueous solution and a Cl minus ion in aqueous solution. So here we would say that the hydrochloric acid has behaved as an acid because it's given away an H plus, and the water has actually behaved as a base. With this new definition, it's a bit like redox reactions. You can't have redox is passing electrons on, so you can't have something losing electrons without something gaining electrons. So it's the same here. You can't have an acid without there being a base, because H plus ions by themselves, they can't exist. They can just be passed on to other things. Now, I know this reaction is, HCl is a very strong acid, so it's not really an equilibrium, but it does have some, there is a tiny amount which will be undissociated. So let's just think as equilibrium for a minute. Imagine if this reaction was going backwards. In this case, the H2O, that would act as an acid, so I'll call that acid 2, and the chloride ion will actually act as a base. So I'll call that base 2. And so we can see that they match up. I'll call that acid 1. Sorry, I'm going to call that base 1, base 1, and call that base 2. Okay, so these two things here, this acid and this base, acid 1 and base 1, these are called an acid-base conjugate pair. Conjugate pair. And there's another acid-base conjugate pair here, is these two. The water and the H3O plus, they're an acid-base conjugate pair as well. Now, what is the definition of an acid-base conjugate pair? It's useful, you can probably see what it is, but it's useful to have a little definition of it. Acid-base conjugate pair are a pair of species. So chemistry, species is a thing, molecule, ion, whatever. A pair of species which can be interchanged by addition or removal of a single proton. Okay, that's our definition of an acid-base conjugate pair. Right, let's have a think about some more reactions, some other reactions. So let's think about ammonia dissolving in water. If you get ammonia and you dissolve it in water, we know that that forms an NH. This is an equilibrium reaction, because it's an equilibrium. You get NH4 plus and OH minus. So where are the two acid-base conjugate pairs here? Well, we have got, let's color code it. So we've got NH3 and NH4. They're interchangeable by addition of a single proton, aren't they? So we're going to call that one. That's the base, isn't it? Because that accepts a proton, base 1. So that will be acid 1. That's its pair. And then the water here, well, that water is acting. It gives away a proton, so that's acting as an acid. So we'll call that acid 2. And there's its conjugate base, base 2, the OH minus ion. Right, let's have a little think about some other species, and we'll talk about acid. So if I put a little table here, we have we'll have acids, and we'll put their conjugate bases here. Right, let's start off with HCl then. Remove a proton for that, what you get? Cl minus, don't you? Let's do water. Remove a proton from water, what do you get? OH minus. In actual fact, if you like, what you can do is I'll fill these in, and then you can pause the video, and then you can see how many you get right. Okay, so I'll do some stuff here. Okay. Okay, so you want to pause your video now, and then I'll put the answers in. Okay, so you unpause your video. Let's see. Acid, right, this one, H3O plus. That loses a proton. What do you get? You get H2O. NH3, add a proton to that. What do you get? NH4 plus. HCO3 minus, add a proton to that. Well, you get H2CO3, which is called carbonic acid. And now HCO3 is acting as the acid. Remove an H plus from that. What you get? You get CO3 2 minus, the carbonate ion. This is the ethanoate ion. Stick a proton on that. You get ethanoic acid. And this is methylamine. Okay, that's a base. So stick a proton on that. Well, the proton goes on the nitrogen because it's got a lone pair on it. So you get CH3 NH3 plus. Right, and then a couple of weird ones. Right, if you've done the benzene topic already, you'll remember when you're nitrating benzene, do you remember you use conc sulfuric and you use conc nitric? You mix them together, and what happens is, so the sulfuric becomes that. So the sulfuric acts as an acid, and it's lost a proton, and very strangely here, the nitric acid behaved as a base, didn't it? HNO3, concentrated nitric acid behaving as a base. Stick a proton onto that. What's its conjugate base? Is H2NO3 plus. Yeah, and that, remember, that decayed to form the NO2 plus ion there. Okay, so hopefully that has given you an idea, a new idea of acids and bases. So it's things, and I suppose it's analogous to redox, isn't it? Redox, you're passing electrons on, losing electrons, gaining electrons. Here you're gaining or losing protons.